Miniko, can you see the screen?
We can see you.
I did. All right, something's happening, but not quite.
I don't know, our screen is black.
So, doesn't look like, right, Miniko? You cannot see the page.
No, we can't see anything.
Or can they see? I'm not sure.
It's black. Goodbye.
Do it again.
Okay, we can see your screen, but we cannot see you, which, I mean, is fine, I suppose.
All right, Miniko, I'm not sure. Can you see the screen? Yes.
Yes.
And I don't know if they can hear me, but I can see they see the screen. All right,
We can hear you.
let's go with that.
Miniko, will you guys respond again?
We can hear you.
Just
We're
going
getting
back to
low.
what we had last time. Now remember we talked about the area or areas between the curves. And the formula or the process is very simple. We just said integral, and then we said f of x minus g of x dx, right? So overall, the top minus the bottom. That's the idea.
Yeah, okay.
Now, in order to find the area between the curves, we have to graph, because
Yeah,
we need to
yeah.
know, first of all, which one, the function, which one's on the top, which is on the bottom. And also we need to know the upper and lower limits. For this example, this was our last example. So when you sketch with graph, we get this shape right here, and it's important for you to know exactly what area you're looking for. Not like, maybe this or maybe that. It's, this is what I know, this is what I'm looking for. So here's the area that we're looking for. So if we follow this process, we should recognize that on the top we have just square root of 2x plus 6. That's just this piece. But when you look on the bottom you have two curves. So on the interval from -3 to 5, speaking about the furthest right distance that we can see here, we actually have two curves. We have this curve and we have this curve. So that means we cannot do this problem just using one integral. We have to split this. So we have to split the integral from -3 to -1, and that's what we have right here. So we have the top minus the bottom one. And then moving to the right, you still have the same curve on the top, but this time minus the line. So by doing this, we arrive to this. So we just simplify this a little bit, not much, because you have negative, negative gives you positive, so you get two square roots. And just, I open parentheses, this is what I have. So now, the only thing, maybe one little thing we can do here is to move this 2 and put it in front of integral. So we get 2 integral from -3 to -1. And then we get square root of 2x plus 6 dx. And here, well, nothing really you can do. We'll be copying this problem. All right, so this is what we have. So overall now I have to find two integrals, this integral, and this integral has to be done by substitution. What is your substitution for this?
2x plus 6.
2x plus 6. And then you do the substitution, find what d over dx is, which is the derivative, right? Change upper and lower limits, we talked about this. Find this integral. Moving to this one, well, probably we have to split this into two integrals. One is just, again, the square root, so still going through the substitution. And then we have just integral of this piece, which is very easy to find, right? Just going through antiderivatives. So that's what would you do if you decided to continue with this. But why I'm not doing this, finishing, because there's another method and easier. So I don't want to do it. You see, I'm stubborn here, saying I know another way to do it, and it's much easier than this way of doing it. So let's take a look, and let's just see how we can do this using different way. So what is different way? Well, different way is just how you will look at the picture. And I kind of mentioned this last time, but obviously I didn't get to the end, that you can look at this picture from this point. So when you look at this picture from this point of view, what do you see? If you go down like this, you see only one curve, and that's our line, right? And then on the bottom, you also see only one curve, and that's our parabola. So when you do this, you will have only one integral. So obvious, if you look at this problem like this, it's much easier because you do not have two integrals. But this time it's not going to be dx, it's going to be dy. And that's what we have to look at right now, or look for, when we see something complicated and we feel like, oh, well, I'm getting two, for example, integrals, but I want to go with two, then maybe you should switch and see, maybe it will be easier for you to go with dy. So let's take a look at this from dy point of view. So as I mentioned, you rotate this counterclockwise, or you keep it the same way, but go from right to left, and this will be the first function, and this will be the second function. So if we are going with dy for this problem, okay, I'll probably continue with this paper. If we're going with dy, now I'm going to put equal one in question, equal sign in question mark, because we will get it, okay, just using different method. So if we go with dy, that means my y is the variable, right? So every function that I have, let's say y equals x minus 1, and y squared equals 2x plus 6, I have to solve for x. In that case, y is the variable. So here, what do we get? What is x from this one? What do we have?
1.
Y plus 1.
So we get y plus 1, right? So this is what I need for this one. And for this one, I also need to get x equals, right? So I have 2x equals y squared minus 6. And then I will divide by 2, and I will divide each of them by 2. So I have y squared over 2 and minus 3. So you just switch the variables, but now you have different functions, because as the look, I'm not saying when you graph it it's the same, but as the look we have different functions. And now we will go and create new integrals. So our area will be integral. We'll come back to upper and lower limit in a moment. But overall, if I put the picture back, let me slide this. If I put the picture back, and as I told you, we'll go from right to left. So first I have the right equation of my line, and we said this is y plus 1, equation of the line, and then minus this one piece, and that's your parabola. So minus y squared over 2 minus 3 and dy. So now if you look at this, we're going to simplify a little bit more, but overall very simple polynomial. The question is, what is my upper or what are my upper and lower limits?
5 and negative 2.
Well, we're talking about x's or y's.
So it would be 4,
So, keep talking.
that'd be 4, -2,
Right, so what do I put over here?
-2.
-2, that's right. And here I'll put 4. So since I'm switched, I still have the same points, okay? They didn't go anywhere. It's still -2, -1, -2, and it's still 5 and 4, right? Same points. But since I'm going with dy, I have to pick y coordinates. So I'm going to use this and this. Okay, have to go with y. And this is my integral. So the picture is the same. The idea is the same, just direction is different. And this time is dy. So you'll be facing the same thing when you will be working on your homework assignments. And on the exam too, where you have to decide if you want to go with dx and dy. And it's your decision, okay? Here, for areas between the curves, you are making the decision. You want to have smaller? Well, maybe look from a different point of view. So to finish this, we have -2, 4, and here we'll have y minus y squared over 2 plus 4, negative, gives you positive here, plus 4 dy. So this is my integral. All right, so let's talk again quickly what just happened. Basically, by doing this, switching to dy, I gained 2 good things. One, I'm working only on one integral. And the other one, look at my function. I have polynomial. It's very easy to find antiderivative of polynomial, comparing with the x version, where I have to use substitution, twice basically. So we have to kind of be careful here not to get into big trouble. It's still doable with x. It takes forever, but it's still doable. So let's just find antiderivative here. So we have y squared over 2 minus what? Y cubed over 6 plus 4x. And we have from -2 to 4.
We'll get 18.
So we'll get 18, you're right. So we're going to substitute as we were doing before. So I have 4 squared over 2 minus 4 cubed over 6 plus 4 times 4. And then we'll subtract and we'll substitute -2. So you get -2 squared over 2 minus -2 cubed over 6 plus 4 times -2, and the answer will be 18. So going with dy, faster, easier, and it's not that complicated. Do you see the idea? Okay. So finish writing this, and we'll kind of talk about some functions right now for a moment, just to give you the idea. Now, this time I had the advantage, okay, again. By going to dy, I changed this to only one integral, and my function's much easier. There's no square root. I don't have to go to substitution. So, for example, and don't write, we'll just watch. So, if my function's something like this, let's say on the top I have, and on the bottom I have something like this. Let's say. So this is my area that I have to find. How many integrals, let's say, do I have to create to find this area if I go with dx?
3.
3, right? Because again, how many functions on the top do you see? 1, right? Then what? 2 and 3. And on the bottom, how many do you see? 2 functions. So 1 is over here, so first you find the area of this, right? Then you split over here, there will be the next area, and that will be the next area. You understand? Now, if I have the same picture and also I will flip it this way, well, it still will not be one integral. Do you see that? At least even just over here, if ignore this, but just take a look over here. You have 1 on the top, right? But at least you still have what? These 2 on the bottom, so you must split it anyway, right? So in this case, I'm not gaining any advantage and actually getting more complicated because of this piece over here. So even if I know I have to use 3 integrals, I will still use 3 integrals going with dx, okay? So that's this. And for example, on the homework assignment, you will have a question to find the area between 3 points, and you know what that is. It will be the triangle, right? So if I go with, for example, dx, how many integrals? Remember, dx means what? Top down, right? So how many integrals do I get? 2, right? I have to split it in this way. So this will be first integral, this will be second integral, right? Do you understand? Because you have 2 functions on the top. Now, if I have the same picture, let's say, and I want to go with dy, how many integrals do you get?
Still 2.
Still 2, right? Because you have to split it like this. First and what? The second. So there's no advantage for me to switch to dy. And actually, if I switch for dy, I will have more work to do. Why? Because all equations that I have of each line, right here, the side, I have to switch to x equals. So for me, it's better to stay with dx. So those decisions you have to make, okay? Those decisions you have to make. And by the way, I just mentioned about this problem. On the homework assignment, it will say, here you go, 3 points, find the area. Now, in order for you to find the area, you must have what? Equations, right? It means you have to find the equation of each line or segment, we can say, and that's where you have to find the slope and use point slope or slope intercept form and to get this. So these things we have to look at. Maybe quickly one more related to this, okay, just quickly one more. And then we will go to the next one. We have to kind of move on a little bit faster. So let me see where I have that function or functions here, just to kind of refresh this again. So if I have something like this, let's say I have, and I don't know, what is this number if I continue? This will be 4? All right, thank you. So I have x equals y to the 4th, first function. And the other one is I have y equals square root of 2 minus x. And the third one I have y equals 0. So if you want to graph, let's say, all of them, well, you have to change this to y equals, right? So you get what? What do we get? How do I get y out of this?
Plus or minus 4th root.
Don't forget plus or minus, that's right, 4th root of x. And these are perfectly fine. So let's just graph with the calculator quickly and see what we get. So if we go with the calculator, we have plus or minus, so you have to write it twice, okay? Now 4th root, I think you can do it. Well, let's take a look. I think, let's see, 4, and then if you go to math, you go down to 5. I think this is what we're looking for of x. Okay, I shouldn't open parentheses, but let me graph this and see if this is the case, if it's going to work, okay? All right, kind of works fine to me. Okay, so let me go back. Then I have negative 4th root of square root of x. Then I have square root of 2 minus x. And, well, if I put y equals 0, I'm not going to see it because it's just x-axis. But anyway, if I graph it, this is what I have. Then I have the little curve. So this is how it looks like, but I really have to zoom in. It's too small. So this is my first curve. That's this one now. All right? So here's my question. If I sketch this picture right here, where is my area?
From 0 to 2.
Okay. And when you say from 0 to 2, where exactly are you looking? Describe.
That semicircle-ish thing?
Semicircle-ish thing right here, right?
Yeah.
Okay, good. That's the right answer. So when we go to the area, my area is right here. Now, it just happened, it looks like area under the curve, but that's not true. Because what do you have? Here's your piece for x to the y to the fourth, right? That's this piece. Here's your square root of 2 minus x, but also it says y equals 0, and it's right here. You understand? That's why we have this area. So here's my question. Let's take a look. I'm looking for this area. And this point right here, we can put 1, 1. Okay, that's the point that I have. So is it good for me to go with dx? What do you think? Is it good to go with dx? And again, when I say dx, what I mean? Top minus the bottom. Can I do it? Well, the answer is yes. How many integrals do I get? I get 2, right? One will be from 0 to 1, and I have this minus this, right? You understand? And the second one will be from 1 to 2, again this piece minus this. Now these integrals are very small, so that shouldn't be a big problem, but at least 2 of them, right? Okay, so if I go with dx, I will have 2 of them. Again, top going down. So 2 functions on the top, only 1 on the bottom. But when I flip it like this again, so what do you think if I go with dy? How many integrals do I have? Only 1. Because I have only 1 function here and I have only 1 function here. Can you see that? So again, it's just easier to go with dy. But also what else will happen? Let's take a look. Remember, all your functions might be switched to x equals. The first one works already. So I have no problem with this function. Okay, I'm going to use it. But this one must be changed. So this function, I have to square, right? I have to square, so I get y squared equals 2 minus x. Because I'm solving it for x, right? Solving it for x. So what is x? When you solve, what do you get? What is x?
Minus y squared.
2 minus y squared. So I'm going to use this one. All right, so now let's do it. So area equals integral. We'll put upper and lower limits in a moment. But remember, I go from right to left. So I have to work with this curve. And this is the one right here. Okay, that's the one. So I have 2 minus y squared. And then I will subtract that. The second one, right, this piece, which is what? X equals y to the 4. So again, 2 good things. Not always we'll have 2, okay? But overall right now we have 2 good things. Again, only 1 integral and no square root. Square root was changed. And again, I have polynomial. So I have 2y minus y cubed over 3 minus y to the 5th over 5. And it's from, okay, now we have to go back and put our upper and lower limit. From what to what?
0 to 2.
Is it dx or dy right now?
dy.
dy. Huh?
Negative 1 to 0.
Why is it negative 1?
Because it rotated, I guess.
And what do you see? Where's the beginning? Where's the beginning? It starts from 0, right? Here's your beginning. And then goes to 1. You see? From 0 to 1. To 1. From 0 to 1. So we have from 0 to 1, and again we have from 0 to 1. So it's nice to substitute. We get 2 minus 1 over 3 minus 1 over 5 minus 0 when we substitute. So when we add and subtract and put everything together, LCD will be 15, so we get 22 over 15. And this will be the answer. All right? So I don't know what's really difficult here. If you look, maybe just to make the right decision to go with X or Y. That's one thing. But if you look at the functions, functions are very simple. They're not that complicated overall. And integrals are simple. But the picture is important. Okay, the picture is important also to know how many functions you have and how you're going to go, and just to make it easier. Okay, so that's about area or areas between the curves. Well, still every problem is different, so I can't say like it's always this way. Well, the general idea is here. So that's about area. So now let's go and talk about volumes. And I know I'm not going to go far, and that's perfectly fine. We'll come back on Monday and still work with 6.2. But we have to begin. So 6.2 will say just volumes. Now, I had, and I don't know if anybody else, I think not in your class, but I had some in other classes, students asked me this, like, okay, so when you say volumes, it means 3D. Does it mean now we have to involve Z as the variable? Because it's 3D, right? Well, the answer is no. Because what's going to happen, we are working with the volumes of revolution. So revolution means to rotate. Okay? So in this case, I don't need Z. And we'll calc 3 that Z will come in when we start doing some different shapes, okay? But right now it's just a revolution, so we will rotate the curve. That's what's going to happen. But before we actually get to examples, let's just get the general idea how we actually get the volume concept with the rotation. So let's start with this. Let's say we have a curve on interval A and B. And let's say this is the curve that we have. And that's your function, y equals f of x. Now, this curve will create area under the curve, okay? Like we kind of had before. So again, this curve will create an area under the curve. And what do I have to do, for example, like right now at this moment? I will take this area and start rotating this area about the x-axis. So I'm taking this area and starting rotating this about the x-axis. Now, it's not that difficult to see what shape you will have. The problem is to make the good picture here. That's the difficulty. But let's say we have something like this. So when you rotate, obvious, we're getting something, volume E. I don't know if I can say that, okay? Maybe I made up something, I don't know. But we get a volume, okay? But what are we rotating again? You're rotating the area, right, under what? The curve, right here at this moment. Now, we also can rotate area between the curves. We'll see that example, okay? But overall, we're rotating the area. So when I rotate this, okay, when I rotate this, I will get something like this. Okay, this shape. Now, but I have a question to you because, you know, normally when we say volume, we may have a little bit different ideas. But is this entire piece right here a solid piece or there's a hole inside? What do you think?
Hole inside?
It should be.
How do you get a hole? Like, what did you rotate?
You just rotate the line around, but
No, you just missed it. What did I say we have to rotate?
oh, the area. Okay.
We have to rotate the area, right? So area, when you start rotating this wall, will fill in the whole thing, right? So you don't have a hole here. It's a one big brick, okay, solid piece. It's one big solid piece. So this is what we have. So this is what we'll be working with. Taking the area under the curve, let's say, or between the curves, and rotating them. Now here I rotated about the x-axis. But technically I could take the same curve and also rotate about what? Y-axis, do you understand? Or I don't have to rotate this about x-axis. What if I want to rotate this about y equals 1? See, axis rotations will change, and that will be difficult part. not about x-axis or y-axis, but when my axis of rotation will be moved. So this is the idea. Okay, you get the curve or curves, define the area that they will enclose, and rotate that area about x-axis, y-axis, or some other lines, okay? And then try to find the volume. So the question is, well, how do I find the volume? I understand how picture works, right? Do you have any problems with the picture? Do you understand how picture works? All right, so the question is, well, how do I get the volume, okay? How's that going to work? Well, let's talk about this. And I will redraw some things. I want to make sure you understand the concept, because you may forget the formula, but if you remember the concept, you will never get it wrong. So look, I have this from A to B, and I have this picture, okay? Kind of trying to copy, maybe almost the same, not exactly, but almost. So I'm rotating this area, right, about the x-axis. I'm rotating this area. Well, remember how we found this area? What did you do to find the area before? Take the integral, right? But what was the integral?
Antiderivative.
Okay, but even before, in section 5.1, let's say 5.2, what was the integral?
The area.
Yeah, we're going back, but not, well, yeah, it's always the area algebraically, all right, concept. But what was the integral? Equal to what? Because you still have this on the exam. It will be the limit of the Riemann sum. Remember? Limit of the Riemann sum. Now, where did that limit of Riemann sum came from? It came from the rectangles that we try to put in, right? So look, if I decided to fill in with a lot of rectangles, now obviously I can't do a lot, but at least to show you. So, for example, I'll go from the right. So you have this piece, right? You get this, then you get this. For example, you get something like this, okay? Putting all of these together, you have to be careful knowing that you're going from the right. So let's say you have something like this. So this is my area. And obvious, again, remember I said limit. So what that means? Infinitely many rectangles, yes? N is approaching to infinity. Well, kind of now visualize this. Let's take all of those rectangles, like what they position right now, all of these rectangles, and start rotating this about the x-axis. What do you think you get when you start rotating rectangles?
Cylinder.
You'll get cylinders. And technically, when you get cylinders, now, I believe you understand, right? When I start rotating, these will become round things, right? Like discs, right? Do you understand that? All of them are cylinders, okay, when I start. So basically, what do I get when I start rotating? I'm not going to do all of them. It's going to be too messy. But basically, this is what I will get, right? Yes, no, for one of them? Well, so how do I get volume? If you use the same idea as we did for the area, what? Find the volume of each one. Cylinder and add them, right? Yes, no. So that's why this is also the integral. Because I can describe the same process here, finding volumes, and still using limit, because I will have infinite number of what? Cylinders, right? Put in. If I have n is approaching to infinity. Here I have what? N is my number, or number of what? Numbers of rectangles, right? But I can say n is what? Number of cylinders, right? But the volume here is just the limit. N is approaching to infinity. And then I'm going to use sigma. Remember I said what? Riemann sum, right? Sigma. I equals 1 to n. But remember, this time I'm not adding the areas. I'm adding volumes of each cylinder. So, now keep in mind, we used to have cylinders this way all the time, right? Something like this. I know it's flat, but it's still cylinder, right? Now it's cylinder on the side, but the height is still over here, right? This is the height. And these are bases, yes, no. And each piece over here is still delta x. Remember delta x? Each piece is delta x, delta x, delta x. So what is delta x? It's the height of the cylinder. But overall, what's the formula for the volume of the cylinder?
Area of the base times the height.
Area of the base times height, right? So your height is always the same. That's your delta x of the cylinder. One more time. This is your delta x over here. Okay? But then we just said what? The area of the base is what? It's area of a circle here, right? Do you understand? And when you keep cutting it, no matter what, it's still the circle, but just different size, right? One smaller, one larger. Do you see this? Yes, no, when you start feeling this thing. So here, this is your height, but here is the area of the base. And normally we put it like area and x sub I with the asterisk. So, but this piece over here, it's the volume of a cylinder. One cylinder. When you add them, you will get a lot. So one more time. We are adding lots of what? Volumes, right? Each volume when you rotate. And here, delta x is the height of each cylinder. It's all the same, right? Delta x is the same, remember. And here is just a cross section, area of a cross section, and you're getting area of a circle. But again, the size is different because how curve goes. So the question is, all right, that's nice, but what do I do with this? Well, what do you do with this? You know from the area that this is the integral from A to B, integral from A to B, then A of x. So what is A of x? It's the area of a cross section. So here this will be area of a circle. But remember, each of these over here have different radiuses, right? So that's why it's A of x. It's not always 5. Every time you start moving, the curve will change. And the radius is different, right? All the time. And dx. And that's the idea of the volume. That's it. Now, we're talking about volume of revolution. That's one thing, okay? I'm not talking about some strange shape. Or, not the revolution, but every time when you slice it, you'll get the same shape. Okay? For example, I don't know. Let's think about what? Let's say you're buying a core, okay? So you have a core. Well, when you start slicing it, it's all the time what? A circle, right? All the time. But it's just different size circle. Do you understand? Okay? What else we have? For example, I don't know the name of that candy, okay? I don't know. But it looks like triangular prism. Check your name. So it looks like this.
Oh, Toblerone.
Right. Well, if you think about this, now we do have a formula for this in geometry. But when I start slicing this like this, every time when I slice this, right, I have the same shape, which is what? Triangle, right? You understand? Or somebody decided to play a little joke. Instead of having nice triangular prism, they decided to create something like this. And this is a triangle. Well, basically it goes like this. But all of this right here is what?
That's disgusting.
Triangle. Okay, you know what I'm saying? I know it looks weird. You understand that? Yeah. So here it's what? Thinner. Here's thicker. Oh, you know what I'm saying? All of this. But when I keep slicing, I'll get what? Triangle. So this formula works as well. It's just what we have as the cross section. It has to be the same. Okay? It has to be the same. You cannot go from circle to triangle and all that, because in that case you have to split them in different pieces. So that's the idea. So idea is not that difficult overall as to apply. So again, let's go back to the formula when we're looking for the volume of revolution, okay, or having the same slices. What do we have? We have integral from A to B. That's the interval. And then we have A of x. And what is A of x? A of x will be the area of the cross section. And here I have a circle because I'm rotating. Here, my area of the cross section is triangle, so I have to find the formula for the area of triangle. Here again, triangle. So that's the idea that we have to work with. So let's go to a very simple first example and see how this can be done. And let's see how far I can go. So example number 1. Let's say I have a function, y equals square root of x, and I have to find the volume, okay, I have to find the volume on interval from 0 to 1, and I'm going to take this about the x-axis. Okay, so when we go to calculator, let's say quickly, and I put this function into my calculator, I'm going to delete all of this. Oops, I missed that one. So if I put my square root of x into the calculator, well, obvious, you see when we graph, this is what I have, the curve, right? And it goes forever, and that's why I have this from 0 to 1 to limit it. So here's my curve, and let's say this is 1 over here. I know it's not exactly correct, but that's what I have. So what do I have here? I have this area over here that I have to rotate, and I'm rotating this about the x-axis. Do you understand the picture? Yes or no? So when you rotate this about the x-axis, again, you'll get this shape, and this will be solid piece, one nice solid piece when you rotate. But here's my question. What is your cross-section? Let's say you took a knife and you decided to slice this, and you're slicing and slicing a million times. What is the shape of the cross-section?
Circle.
Circle, right? So you'll get a circle right here. And this is just one cross-section, right? I'm not going to put a lot of it. This is what I have. Now, why do I need this? Because I need to know what A of x is. That means what? Area of this circle. So my question right now, if I go from axis of rotation to the original curve right here, what will be my radius? What's the measure over here?
Square root of x.
It's square root of x. It's not 5, it's not 2, it's what? Distance to the curve, right? Distance to the curve. And the radius will be, radius equals square root of x. Again, not as a number, but actually as a function. Why? Because remember what I just told you. You will have multiple slices, and each slice has different radius. You understand? When you start slicing it, okay? That's why it's not 5, it's not 2, but it's square root of x. It's related to the function. And then a of x as a function, knowing that I have this as a circle. Let me take away the calculator, we don't need this anymore. So area is pi r squared, right? Because it's a circle. Now what is your radius? We just said what?
Square root of x.
You get square root of x and you will what? Square.
Just get pi.
So we'll get just pi x. So you know what the area of the cross section is, and this is your A of x, and then you just go to the integral, and you have what? Pi x what? Dx. Now one thing what's left is to determine the upper and lower limit, right? Well, it's easy, because you go from 0 to 1. And this is the setup for the problem, okay? This is the setup for the problem. So, pi, and we have x squared over 2 is my antiderivative. So you go from 0 to 1. So you get pi 1 over 2 minus 0. So the answer is what? Pi over 2. Now you should expect to see pi, let's say all the time, because again, you're rotating, you're involving circle. So you don't give decimals here. Every answer that you will get will be with pi. Okay? Except when I just said when we have triangle, then you don't get pi, okay? But here we get pi. Did you get the idea, general idea? Yes, no? Do you understand? All right, let's take a look at a little bit different one. And like I said, I will not present the entire concept today, but we can still pick up something on Monday, and maybe I will not give you this assignment due next Tuesday. I will extend, that's fine, I don't care really, but I want to make sure you understand this. So let's say we have another function or functions, and we have y equals x squared, and you rotate this about the x-axis again. Okay, so let's go quickly and graph this. So I have x, one function, then I have x squared, the other function. And when we graph this, so this is the line, and this is the parabola. So by looking at the picture on the calculator, like, where is my area that I have to rotate?
0, 1.
Okay, that's the interval, right? But the picture of the area, how does it look like? Where is it?
That little slug.
The little thing, right? That's right. Because we're still thinking about what? Area enclosed, right? You understand? Still thinking about area enclosed. So when I go to the picture, what do I have? I have my x over here, and I have my parabola. So this is what I'm getting. You understand? And it will be from 0 to 1. That's absolutely right, because the intersection here is 1, 1. So this is the area that you will be rotating. Now, don't forget, we said we're rotating these about the x-axis. And honestly, you know, I really don't care if you rotate over here and show me how it's going to look like. Now, we know how it's going to look like, okay? You have this, and then you have this piece, okay? So this is how it's going to look like. Of course, it's what? 3D, right? You understand? If you rotate, you're getting something like this. Now, this actually shape has a little hole over here, right? It's not like solid piece like we had before, okay? But here's my question. If I slice this right now, how is my cross-section going to look like? How is that going to look like? If I take a knife right now, I'm just going to slice it. How is it going to look like?
You like a ring, right?
Right, we call it washing.
Okay.
Right, just the washing. The previous one, if you look over here, I didn't tell you this because I was waiting for this problem. This one we call a disc. So this is a disc because it's solid, and this will be a washer. So when we go with the washer, if you still don't see it, it's going to look like this. Okay, this piece and then the inner piece. So overall, you'll get something like this. Okay, that's what you're looking at. So where the difficulty will come in right now is to figure out the radius. And overall, as the concept, what do I need to know right now? I need to know the area of this cross-section, yes, no? An area of this cross-section is your washer. It's right here. How do we find the area of a washer? Describe.
Take the area of the bigger circle.
Right, so but we're speaking about what? Area, right? So you find the area of the largest, right? And then subtract the area of what?
Small.
The smallest. So, A of x, pi. So here's my question. What is the radius of the larger circle?
X.
It's what? The distance from the axis of rotation, from this inside piece, right? To what? To outside. And this will be x, that's right. So you get x what? Squared. So this is the area of the larger circle. Minus the area of the smaller. So what's the radius for the smaller? It will be x squared. So you get x squared and squared. Well, if you do this, you get pi x squared minus pi x to the 4th. And this is here the function that you have to work with. We're almost done. Let me just refresh one little thing here, just in case if you didn't see this, okay? I want to make sure you see it. So, and I know how big I have to make this. So this is my line, and this is my curve. Okay, let's say something like this. Well, I have the same thing on the bottom, right? And I am rotating this about the x-axis, right? So you're getting these pieces, again, something like this, and then you have something like this. So we're looking for the distance, right? So distance from here to right here is just the distance to the curve, right? That's it, which is x. That's why we put x squared. With this one, distance will be what? X squared, right? Like we just said before. So you'll get that. Well, and we're ready to substitute into the integral. So, can we factor out pi?
Yes.
Here's the function, right? Can we factor out pi?
Yes.
Right. So we factor out pi, so volume is pi, integral, and what do we have? X squared minus x to the fourth dx. What about my upper and lower limits? Let's go back. So from 0 to 1, right? From 0 to 1. Well, very simple integral to find. So we get x cubed over 3 minus x to the fifth over 5 more dx, sorry. From what? 0 to 1. If we substitute, we'll get 1 over 3 minus 1 over 5, and obviously we get minus 0, right?
If you would like
I'm not going to write this.
are due today, you can
So, but when we finish working on this, what do we get?
Or Miss Smith as well. And we would really like it if a ton of people would come.
We get 2 pi over
event for everybody. That'll be on the Tuesday when you come back from Thanksgiving break.
And
during
that's the
Thanksgiving
vote.
break, we'll have a canned food drive at Century Cinemas. That will be November 24th, and the showings are
So
at 9
I didn't show you a lot. The only thing what I really showed you, I showed you rotation about the x-axis with 2 different pictures. One with the solid piece inside, as I said, a disc.
And the movies are
And this one I showed you with the wash. Now what's left? Well, I have to show you how to rotate about the y-axis.
We also want to remind you guys
Right.
to come out to that.
And also I have to show you how to rotate if your axis of rotation is not axis or y-axis. It's shifted up or down or left or right. That's what I have to show. So that will be on Monday. And that's what I said, Miniko. I don't know. Well, if you have a chance to watch it, watch it. Notes will be online, but please read the book. Read the book. There are good examples in the book, good pictures, and you should be able to grasp the concept. But I will be talking about those things. So it's not just today. So we'll get more of this. So, have a good weekend, and I'll see you on Monday.
Because we have to find an